So it's time to take a look at our third and final case for end behavior asymptotes. And in this case, again, if we look at our lead terms, we're going to have a lead term of 5x squared and a lead term of x in the denominator. And if we rewrite that, we'll get 5x squared over x. And that can be reduced to 5x. So the behavior of this very complicated fraction will behave in the same way as this for large values of x. So as x approaches infinity, what happens to 5x? Well, if you put a really large number in here and multiply it by 5, it's also going to get very large. So we're going to say that this approaches infinity. The same thing will happen on the left-hand side. So the left-hand behavior will look the same for large values of x, but negatively, this is going to approach negative infinity as well. So this is a little bit different. We don't have a horizontal asymptote here. We have a different kind of asymptote here because we have this thing approaching infinity and negative infinity. But it does that in a very special way. So we want to figure out what that very special way is. To know that, what we're going to do is we're going to come back to this original function, and I'm going to rewrite this function in a little different way. I'm going to rewrite this function by actually performing this division. I'm going to take 5x squared plus 3x plus 1, and I'm going to divide it by x minus 2. To do that, I'm going to choose to do this one synthetically because I can divide synthetically. In this case, had I not had this been an x squared or an x cubed or something, I would have to do that by long division. In this case, though, I can go with synthetic division, so I'm going to put a little 2 here, and I'll write 5 and 3 and 1, the coefficients of the dividend. And then I'm going to, as we do with our synthetic division, I will bring the 5 down. I'm going to multiply and add, and multiply and add. Now this final number is the remainder, so this function f of x can be written in a different way. F of x is exactly the same as 5x plus 13 plus 27 over x minus 2. Now again, end behavior is really what we're interested in, and this function that I've just rewritten is identical to this function right here. I still want to see what happens for large values of x. So consider what would happen, in particular, just to this part of it. If we look just at this part of this rational function, for large values of x, we would have 27 divided by a very large number, which we know that when the denominator has degree larger than the numerator will approach 0. So this thing is going to go away. It's going to approach 0. The remaining thing is a linear function. So for large values of x, this function is going to look a whole lot like this linear function. And we call that its asymptote. Now in this case, we don't want to say it's got a horizontal asymptote because that's not a horizontal line. So instead we say it has a slant asymptote, which I'm abbreviating SA, of y equals 5x plus 13. So let's go ahead now and summarize the 3 different cases that we've learned about. In case number 1, we discussed the case where the degree of the denominator was greater than the degree of the numerator, and anytime that happens, we'll say that this is going to have a horizontal asymptote, and it's going to happen at y equals 0. In case number 2, the degree of the denominator is exactly the same as the degree of the numerator, and in that case, we're also going to have a horizontal asymptote, but it's going to happen at y equals, and I'll just write here the coefficients, but what I mean by that are the coefficients on the lead terms of both the numerator and the denominator. So in the example we saw a few minutes ago, it was y equals 5 over 2. Final case, and the most complicated of those, if the degree of the numerator is greater than the degree of the denominator, then we know it's going to have a slant asymptote or some other end behavior asymptote, depending on what you get with your division. So I'm just going to write here, it's going to have a slant asymptote or an end behavior asymptote. So to find that, we have to really follow a couple steps. And in step 1, we actually have to perform the division, either long division or synthetically division, depending on the problem and what you can do. And then secondly, we have to consider what happens to the remainder as x approaches plus or minus infinity. And what's left over could be a slant asymptote if it happens to be linear. It could actually be something like a quadratic asymptote or a cubic asymptote or something else depending on what happens when you actually do that division. So those are the 3 different cases for end behavior asymptotes in rational functions.